So welcome to my talk about Absinthe. Absinthe is an optimization framework to tune Stencil programs for the cache hierarchy of modern multi-core CPUs. So we apply Absinthe to COSMO examples. COSMO is a regional atmospheric model used by 7 national weather services, and it is just one example for the importance of stencils in scientific computing. There are other domains like seismic imaging where people also use stencils. To begin with, I would like to explain you or give you an overview of the optimization process. On the top right, you see an example stencil program from COSMO with 9 stencils. So the blue bubbles are the stencils, the individual stencils of the program. The arrows show the data flow between these stencils, so input, outputs. And the green bubbles basically show if we fuse 2 stencils. So in this example, we don't have any fusion, so it's an unfused implementation, and the tile size is 64 times 64 times 1 for each stencil. Now what we see is on the x-axis, the modeled execution time, so the predicted execution time by Absinthe, and on the y-axis, the measured execution time. Now if we run Absinthe, it searches the whole search space, which is exponential in the number of stencils, for example, and we get an optimized version. So in this optimized program, we fuse the first 6 stencils and the last 3 stencils, and we have different tile sizes annotated in the diagram. And we can also see that the model prediction and the measured execution times are very close. So this is good news. And if we compare this to exhaustively auto-tuned version, then we see that auto-tuning, of course, is still a little bit better, but not too much, just 6% better in this case. Now, let me start by explaining briefly what I mean by a stencil program. So a stencil itself is basically an element-wise computation applied to a grid. So in each grid point, you perform the same computation, and you usually have you access a constant neighborhood, constant size neighborhood around your grid point. In this example, we have 2 stencils. So first we compute A. We apply apply the stencil to the full domain, shown here, and we perform in this process 1 load and 1 store. Why just 1 load? As you can see, the I offsets are all along the X dimension. That means the data is in the same cache line. While we assume if we have an access in the Y direction that this doesn't fit the cache. So the blue stencil, which runs afterwards, basically has 2 loads because the Y+1 and the Y access different, basically are not in cache at the same time. Now, if we want to tune this, what we can do is basically we split our domain into tiles and then apply the stencils to this tile, basically. You can now see on the left-hand side how this looks like in code. So basically, we introduce a new outermost loop over the tiles. We allocate, instead of allocating our temporary field A, which is written by the first stencil and read by the second stencil, instead of allocating it on the full domain, we just allocate it on the tile size. And to visualize what happens if we execute this is, first we apply the A to the tile plus some boundary because we have dependencies in Y+1. And then we apply it to the second stencil. Then we go on to the next tile, to the third tile, to the fourth tile. And what this does now is that we basically only read the I stencil 1, assuming this tile fits the cache. A is completely in cache, and we store B. So we reduce the main memory traffic considerably. So how does Absinthe work internally, or what components does it have? So first we have a model learner. That model learner runs a set of benchmarks on a target system. So this is only done once for each target system, and learns a performance model. The performance model is then an input to an optimizer. This optimizer, for every Stencil program that we want to optimize, sets up an ILP problem. That ILP problem enumerates the search space. So what fusion can we do? What tile sizes can we choose? And it also basically uses these learned model parameters to compute the estimated execution time for these solutions, and then searches the best code transformations for the Stencil program given the performance model. So it's not the optimal, of course. It doesn't find the optimal code transformations because the model may be imperfect, but it finds the optimal transformations according to this performance model. And then the code generator generates hopefully fast code using the code transformations given by the optimizer. So what are the fundamental ideas behind the performance model? So one approach would be that we observe that stencils are very regular computations and that we basically do the same thing for every grid point. But this is not quite the case on real hardware. So instead of looking at the grid point, we actually look at innermost loop executions. One reason for this is, for example, that the compiler will probably introduce some sort of scalar peel loop. So your domain is probably not a multiple of the vector size. So we may first have some scalar execution, and then once the data is aligned, we switch to vector execution. And at the end, we may have scalar execution again. So as a result, basically there is some startup overhead for the innermost loop execution. And once this is done and we run vectorized code, we have a higher throughput. So we basically have a startup or a latency component and a throughput component. So in the paper, I will call these peel and body components. Then we also observe that stencils are heavily memory bandwidth limited. And by memory, I mean not just the DDR memory, but actually the L1 cache and the L3 cache or DDR, depending on your problem size. So if we look at this example, the black boundaries basically show a stencil. So if we execute this stencil, we first load the blue point from the slow memory to the fast memory. So we have one slow memory access and we have 3 fast memory accesses. If we go further and further, we basically see the same pattern. So we always in every iteration load one element from, or one data point from the slow memory and 3 from the fast memory. That means either of these two will probably dominate the execution time of our stencil. And these are the 2 components we will model in our performance model. So because we want to feed everything in a linear, in an ILP, we basically, because for that we need to have the performance model in a linear form, we basically choose a very simple model which has a peel component, which is this P times B, and the body component, which is uppercase B times lowercase b. Uppercase letters are always constants for in our ILP, while lowercase letters are variables. So variables are, for example, how many cache accesses do we have if you want to model the performance of the cache. And the uppercase P basically translates from number of cache accesses to an execution time. And these uppercase P and B, so these constants, are actually the learned performance model parameters. Now we have 2 of these models. So one, as I said before, one for the slow memory and one for the fast memory. And to combine them, we always take the maximum of the peel costs, of the latency, and the maximum of the body cost for the 2 performance models, the slow and fast memory. And that gives us now, this T gives us the execution time for an individual stencil in the program. but our program usually has multiple stencils. So in the example, we had 9 stencils. So what we do is we basically sum up the times we predict for the individual stencils. So how do we now compute the lowercase b and b? So, or basically, in case of the fast memory model, these are the number of cache or fast memory accesses. The idea is here that we have our domain, and for Absinthe, the domain size needs to be constant or compile time. So the uppercase D and D's basically define the size of our domain. Then we have variables, and the variables nx and y basically say how many tiles we have in x and y, in the x and y direction. These are variables because depending on the tile size we find, the optimization parameters change or the performance changes. So these are actually variables of our optimization problem. Now to compute the number of peel points. So these are cache accesses at the beginning of the innermost loop, and the total number of cache accesses, this is B. We basically use these variables. So the total number of cache accesses in the body domain, so BF is just the product of the 2Ds. And for the peel cost, sorry, for the number, the peel cost or the blue points is just nx times D. Now this is a simple case because we may also have some boundary, or so we have seen in the beginning that we sometimes need to compute outside of the boundary of the tile. So that slightly increases the complexity of our formula. And finally, we also, if our stencil has, for example, 3 loads and 1 store, we need to multiply this points by the number of loads in store to get the total number of cache accesses. Once we have this cache accesses, we can multiply them by the learned model parameters to get an execution time. So this is basically the idea how we evaluate the fast memory model in the ILP. Now, how do we learn these model parameters? So the idea is, again, in the example of the fast memory model, to design stencils that stress that particular memory. And in case of the fast memory, so the cache, the idea is to have stencils which access a lot of grid points. That way, the first access that comes from DDR is not too relevant. So we have, in this example, 3 different stencils with between 12 and 20 memory accesses. And then we basically benchmark these for different problem sizes. So we vary x in this example, but also the tile sizes along the other dimensions. And then we try to fit the performance model. And we do that using least absolute deviation linear regression. So instead of minimizing the squares, we minimize the absolute value between the model prediction and the measured execution time. So here on the bottom, TR is the measured execution time, and PR, BR is the estimated execution time. And as a result, we get our learned model parameter. So it's a really simple form of machine learning. Now, you may have seen that we, in some of the formulas we want to evaluate in the ILP, there are actually products between variables. Now, this of course raises the question, how can we do this? And the answer is, it's possible in an ILP to compute the multiplication if the integer variables are bounded. And of course, it has a high cost because it will introduce a lot of additional variables. So we will see in a second how this works. So the first observation is that we can compute a binary product P that multiplies a variable x with a given upper bound x by a variable b. So b is binary in this case. What happens now is that the result can either be 0 or x, depending on the value of x. So we can introduce a first constraint in our ILP that says that p needs to be between 0 and x, obviously. And then we can introduce two more constraints. The first is there to handle the case where b is 0. So if b is 0, the constraint below basically simplifies to p smaller or equal than 0. So it forces p to 0. That's exactly what we want. And we also introduce another constraint that in case b equals 1, the uppercase x's disappear, and the constraint simplifies to p larger or equal than x. So that forces p to x in that case, in the case that p is 1 actually. Now, this is just a multiplication by a binary variable. So if we want to compute the integer product of two variables x and y, again given upper bounds x and y, we can basically, what we do is we represent one of the variables as a product of binaries. So in this binary representation shown here. And we then can compute p as the sum of many of these binary multiplications. So here we see why we need an upper bound. Basically, we need it first of all in the constraints, but we also need to know how many of these binary variables we need, basically. And this is also the cost of this. So introducing lots of these binary variables has substantial costs when optimizing the ILP. So what are our results? So in this plot, we show basically results for the Fastwaves example or kernel. And the green points are different implementation variants. So different fusion choices, different tile sizes. And on the x-axis, we have again the estimated time. On the y-axis, the measured time. So good news here is that actually most of these different implementation variants are sort of close to the diagonal, which means our performance model works reasonably well for these points. And we see, of course, that Absinthe selects the implementation variant that has the smallest estimated execution time. Auto-tuning finds a slightly better solution. So this is the same result I showed you at the beginning already. And just for comparison, these are the min and max fusion strategies. So fusing all the stencils or not fusing stencils. So they're quite suboptimal in this case. And we also show a hand-tuned implementation variant. For diffusion and advection, we get relatively similar results. So we are always in the range of 10% from auto-tuned results, which is pretty decent. Okay. We also compare our solution to Halide and Polymage. These are frameworks, or respectively to the auto-tuners of, not auto-tuner, basically also a model-based tuner of Halide and Polymage. And these frameworks are optimized for image processing. So we sort of expect that they're not working so well on climate stencils. But still, our advantage is quite significant there. So they are 30 to 60% faster in this case, even worse for advection, a little bit better for diffusion. So we outperform them in all cases, which is definitely nice. So I showed you basically that for stencil programs, the main optimization you do on multi-core architectures are loop fusion and loop tiling. And if you have longer stencil programs, the search space there can be exponential or is exponential. So doing it by hand is difficult, and having some sort of automatic tuning it's definitely a plus. Absinthe learns a simple performance model, a linear performance model, and then uses an ILP solver to select good code transformations. And we showed basically that for our benchmarks, we're close to auto-tuning, so within 10%.